Today we discuss one of the application of Schrodinger wave equation, that is particle in a one-dimensional box or particle in an infinitely deep one-dimensional potential well. In this problem, we study the behavior of one-dimensional motion of particle in a rigid box or infinitely deep potential well by using quantum mechanical treatment. As the particle is moving along the x-axis in between the two rigid walls, which extend from x equal to 0 to x equal to a, that particle is moving without any external force. It means its potential energy is 0. As the particle is moving in between the two walls and it strike at the wall x equal to 0 or x equal to a, the particle will experience very large force, and that time we take its potential infinity. The mathematical representation of a such a one-dimensional box is represented as v of x is equal to 0 for 0 less than x less than a, and otherwise that region its potential is infinity for x less than or equal to 0 and x greater than or equal to a. As the particle is moving in between the two walls, it is independent on time, and hence we use the Schrodinger steady state wave equation. The steady state wave equation or time independent wave equation, it's represented as d square psi of x by dx square plus 2m by h cross square into bracket e minus v of x psi of x equal to 0. By using this mathematical representation, for the region 0 less than x less than a, potential is 0. Therefore, the equation becomes d square psi of x by dx square plus 2m by h cross square e psi of x, since v of x is 0 only for the region 0 less than x less than a. That equation we have to solve here. Here we use 2m by h cross square e is constant. That constant is k square. Therefore, the equation becomes d square psi by dx square plus k square psi equal to 0. Now, we solve that equation, differential equation 2. What is the general solution? We write the general solution as psi of x is equal to a sin kx plus b cos kx. Here a and b are the constant. Firstly, we determine the constants a and b by using the boundary conditions. The boundary conditions are, we write at x equal to 0, function is 0, and therefore we simplify this equation. Psi is 0, sin kx where x is 0 means sin 0 is 0, but cos 0 is 1, therefore we get the value b is equal to 0. If b is 0, the equation becomes psi of x is only a sin kx. Then apply the another condition at x equal to a. This is another boundary where again function is 0. Put the value x equal to a for psi 0. Then the equation becomes a sin ka equal to 0. Now when sin ka becomes equal to 0, that we explain here. Here, whether a is equal to 0 or sin ka equal to 0. But if we choose a is 0, then again what happens? Function is 0. And if function is 0, particle does not exist in the potential well. Therefore, a never equal to 0. Remaining term becomes 0. Sin ka is equal to 0. That is ka equal to n pi. Hence, firstly find the value of k from that equation. K is n pi by a, where n is equal to 1, 2, 3, 4 and so on, where n is the quantum number, it integer number 1, 2, 3, 4. Put the value of k in this equation, required solution for a differential equation which we solve for one-dimensional motion of the particle in a rigid box. The equation is The wave function for the motion of particle psi n x, nth term we write a sine, where the value of k is n pi by a, hence n pi by a x we write for the region 0 less than x less than a. Now we find the eigenvalues of energy. For that we use the value of k, that k is under root 2 me by h cross square and n pi by a. We balancing the two terms and find the nth energy term En is equal to n square pi square h cross square divided by 2m a square, where n is equal to 1, 2, 3 and so on. Here it represents the eigenvalues of energy for n term and it gives the discrete energy levels of the particle. Now we find the various energy states with different energy and we choose the lowest value of n for n equal to 1. It gives the lowest energy or ground state energy of the particle. Its value is E1 equal to pi square h cross square divided by twice m a square. Therefore, the nth energy state in terms of E1, we write En is equal to n square E1. Using that term, we find the spacing between nth energy state and next higher energy state increases by an amount 2n plus 1 times E1. That is, if we suppose n plus 1th term we write and its energy is n plus 1 bracket square E1, and we find the spacing between the nth term minus n square E1, it is increases by an amount 2n plus 1 E1. Hence, if we plot the energy level diagram for nth term, it shows the spacing between the two energy level, it continuously goes on increasing. Now we find eigenvalues of the momentum. For that we use the equation Pn square is equal to 2m En. This is the simple relation for the energy E equal to P square divided by 2m, simplified in that way Pn square equal to twice m En. We find earlier the value of nth energy state. We put here 2m multiplied by n square pi square h cross square divided by twice m a square. Here 2m cancel and we get the simplified term n square pi square h cross square divided by a square. Therefore, Pn is equal to plus minus n pi h cross divided by a. This h cross we simplify. H cross is the reduced Planck constant. Its value is h divided by 2 pi. Therefore, we write plus minus nh divided by 2a. Now, what is the plus minus sign indicate here? Plus minus sign shows the particle is moving back and forth in the potential box, and that equation represent the energy eigenvalues of the momentum of the particle. That values are discrete values for different values of n equal to 1, 2, 3 and so on. And the separation between the momenta corresponding to two energy level is constant equal to h divided by 2a. Now, what are eigenfunctions? The wave functions corresponding to nth energy state is called as eigenfunctions, and it is represented as psi nx is equal to a sine n pi by a into x, where a is constant. That constant is determined by using the normalization condition. Normalization condition is known. What is that condition? Integration 0 to a modulus of psi nx square dx equal to 1. We put the value of psi nx and its square and simplify the equation. We get the constant a. That constant a is under root 2 by a. Therefore, the required term becomes psi nx is equal to under root 2 by a into sine n pi by a into x. And corresponding energies are nth energy state En is equal to n square pi square h cross square divided by twice n a square. Now we have to find what is the actual behavior of the motion of particle in one dimensional potential well or the rigid box in different energy levels. That is represented here. For ground state or lowest energy state for n equal to 1, the function behaves like this is if the function reaches maximum in between x equal to 0 and x equal to a, but on either side of x equal to a by 2, the function vanish. It means for ground state, the psi1 function has the two nodes at x equal to 0 and x equal to a where the function vanish. Then for n equal to 2, psi2 function has three nodes at x equal to 0, x equal to a by 2 and x equal to a. Similarly, we also mention for n equal to 3, there are four nodes. For n equal to 3, there are four nodes. And for nth term, the nth function will have n plus 1 nodes. For that nodes, function is 0. Now we find probability density for one-dimensional motion of particle. Probability of finding the particle over the small distance dx is given as p of x dx is equal to modulus of psi nx square dx. Put the value of psi nx that we calculated earlier and its square 2 by a into sine square n pi x by a dx. Now we find when the probability density reaches maximum for different values of x that we calculate, n pi x by a should be pi by 2, 3 pi by 2, 5 pi by 2. Then only the sign is 1 and probability density becomes maximum. Hence, calculate x separately for different values of n, a by 2n, 3a by 2n, 5a by 2n. Now we for different values of n equal to 1, 2, 3, the variation of probability density with x is shown here. For the ground state, n equal to 1, the probability density is shown here. Probability density modulus of psi 1 square, psi 2 square, modulus of psi 3 square, all that probability density terms are real and positive. For ground state, it shows the probability of finding the particle reaches maximum at the distance x equal to a by 2. Since put n equal to 1, we get a by 2. On either side of that maximum point, the probability density goes on decreasing on both sides and it vanishes at the wall x equal to 0 and x equal to a. Similarly, for first excited state n equal to 2, the probability density reaches maximum at the distance x equal to a by 4 and 3a by 4. Similarly, for n equal to 3, its probability density reaches maximum at the distance equal to a by 6, 3a by 6 and 5a by 6. In that manner, we find the behavior of the moving particle in a one-dimensional rigid box or the deep potential well by studying the different energy level and their corresponding function. If the same problem we study with the classical mechanics, then the probability density is uniform throughout the region and that is shown by the dotted line.